You're still in the cell, and now we're going to move on to cam clip 4, which is a continuation of information about various transport mechanisms. So we just need to now look at what is the relationship between all of this and what does it mean to us in our body. So I know I don't have to really review this, but a solute, is something we dissolve, a substance that we dissolve in a solution, and a solvent is the liquid portion, if you will. When we talk, and I've talked about osmotic pressure, that's the pressure of the particles. So when I talked about the rice would be the osmotic pressure. How much rice in a pot will determine how much water is pulled. If you have, not too much rice, then you're not going to use up that much water. And the more pressure we have, we need more particles or more solutes. Hydrostatic pressure is force. We talked about that, where it's water pushing. Okay, water pushing. Think about it like this. Okay, water pushing. And that's the pressure we talked about from the blood capillaries. Okay, and as it gets to a vessel, a blood vessel starts out large and it goes smaller and smaller until it gets to a capillary, and the capillaries are the tiniest of blood vessels that connect the arterial and the venous side, and in between they're just like hairs, like a hairnet, if you will, and the cells are all surrounded by that. So the smaller we push our blood through the smaller vessel, the more pressure. Think about having a big, like a fire hose, and then you put a smaller hose and a smaller hose until you have a garden hose on it, and the pressure is going to obviously be higher in the garden hose than it will be in the bigger hose. So those are the two things we have to think about. Osmotic pressure is water pulling. What's doing the pulling is the particles. Okay, so the greater the osmotic pressure, or the more pulling we have, the more pulling that we have, then the more pressure. So the more particles, the more the water is going to be pulled towards the particles. Hydrostatic pressure is the pushing. So how fast is the water flowing? Like Niagara Falls versus water flowing in a little creek. So the greater the osmotic pressure in the blood, the more water it'll hold, because the particles create the osmotic pressure and it's going to pull the water back. Sodium, if you remember, is a major extracellular cation, and so the more sodium you have in your blood, above a normal range, the more water we're going to have pulled towards that area and going to cause edema. So when you see people with ankle edema, for example, they might have a high sodium and they might need to go on what we call a diuretic to get rid of the extra salt in water. When in filtration, the gradient is a pressure gradient. It goes from, could be a low pressure gradient to a high pressure gradient. And the substances move then from high to low. So you can imagine you turn on the hose, the water comes out quickly, that's a higher pressure, versus if we just trickled the water out, we would have very much a lower pressure there. Filtration is what the kidneys use to function properly. So they're constantly sieving. It's like putting your water and your kidneys through a sieve and holding on to certain particles that we need in our blood versus things we want to get rid of. So all of this gets filtered out at the capillary level. Because remember that the pressure within the capillaries is greater than the kidney. So therefore we're going to have higher pressure. Both pressures, both osmotic, okay, and remember that's water pulling, versus hydrostatic, which is water pushing, help maintain our intracellular and extracellular fluids. Because to have homeostasis, we need to keep the fluid particles in there the same. So remember, our ICF is what's in the cell, our ECF is the plasma primarily, and the interstitial fluid, and this is 63% of our water, and this is 37% of our water. So what is it that creates pressure for us? So water is our universal solvent in the body. And remember that in that water we dissolve things, solutes, particles. Those particles could be electrolytes or non-electrolytes. So remember that non-electrolytes are things that aren't going to be charged. They're not going to break down. So think about things like they're organic molecules, glucose, lipid, creatinine. Those are not going to let off a charge. Versus electrolytes, which become charged. So we think of things like sodium, potassium, chloride, all kinds of them, bicarb, hydrogen, and these dissolved particles then create the osmotic pressure, both non-electrolytes and electrolytes. So there's still particles in there, and they create pressure. So it's like having lots of ingredients in the soup. The more ingredients in the soup, the higher the pressure is going to be. We talked that water moves towards the moves according to the pressure or the osmotic gradient, and we're going to pull the water towards the particles. And the cell membrane semi-permeable, meaning it allows certain things to come and move throughout it, inside and outside, depending on its solubility, the size, and the speed. So we are constantly mixing and exchanging our fluids because of these two pressures. I alluded to this a little bit earlier, and we'll just go over it a little bit more here. So what happens is water moves between the compartments, the intracellular and the extracellular compartment. When we have fluid at the arterial end, so that's the artery part, so it's come from the heart, the left side of the heart, right? And it's come to a capillary. This is how I draw a capillary. And so this is high in oxygen, and capillary connects us to the venous side, and it's going to go back to the heart, and that's the right side of the heart. So it's here in this area, okay, that they're all tiny little holes in the vessels. Remember, they're just like hair-like thick. And because of those holes and the pressure, water squirts out, okay? And the water squirts out because of high hydrostatic pressure. And the transport mechanism associated with that is filtration. It just goes. Whatever comes out the holes, however big the holes are, is what can come out. And this goes into our interstitial fluids. And our interstitial fluids, remember, bathe our cells. Okay? So it's like the broth, and the water gets picked up by the cells, and the cells take what it wants, like if it needs glucose or oxygen or sodium or whatever it needs. So that creates a little more water in that space. So then what happens is we can't leave that water there. We have to pull it back because we have to have water in our blood vessels to keep, like 90% of your water in your blood is going to squish out here. So we got to suck it back after. It's kind of like a tsunami, you know, it goes over the cells grab what they want, and then it goes back like a wave receding. But what pulls it back is osmotic pressure, because there were particles in that vessel in here that could not get out because the holes were too big. And that creates a high osmotic pressure, and that pulls the water back or sucks it back. Okay, that's the water of our blood. So it leaves because of hydrostatic pressure, water pushing. It washes over the cells, and it comes back because of osmotic pressure. And it is the balance between that, the balance between the pressures of hydrostatic and osmotic pressure, that allows us to maintain the homeostatic range here. Osmosis will continue until the pressure is satisfied according to how many particles are there. And hydrostatic pressure will equalize with osmotic pressure eventually. And that's basically a very important fundamental piece about how our body cells receive their nutrients and various chemicals that they might need. Okay, so that leads us into looking at what is tonicity. So tonicity is the tone of a solution. How stiff is something, if you will. So I could imagine creating a bowl of Jello, and in one bowl of Jello you use too much water to make it, and the other one you didn't use enough water. So you've got different tones of these two different substances, right? Okay. The tone is in relationship to the water and the particles. So in the Jello that you didn't put enough water in, there's more particles, therefore it's stiffer or is thicker, okay? Versus the tone of the Jello you use too much water in, it's looser. It has more water than particles. So where this actually becomes important to us as nurses is when we're talking about IV solutions. Okay, ISO means the same, and it means that on either sides of the membrane, the solutes are the same. Okay, so if I was comparing, just for interest here, two cells, and they each would have the same amount of particles in it. So it would be isotonic, the same. Okay, examples of IVs that are isotonic are normal saline, Ringer's lactate, and we'll talk more about that. As well, if something is hypertonic, it's thick. It has too many particles as the one it's being compared to. So it's the Jello with, not enough water. So if I compared two cells, one would have more particles than the other. Okay, so this is hyper. Hyper means increased or above. Okay, so how something is hypertonic, it has more solutes than what it's being compared to. That's going to suck water to that. If that's your blood, it's going to pull water out of your cells in your interstitial spaces if it needs to. So a hypertonic solution is thick. I like to use those terms thick and thin so that you can have a visual. As opposed to a hypotonic, okay, here we go. Here's a hypotonic. Okay, now this one would be hypotonic because it's hypo means below. Okay, all right. So it's got less than what we're comparing it to. So if we gave you a hypotonic IV, it would mean like you have more water in that IV than particles. So maybe you're dehydrated. We need to make sure you get more water. The osmolality is, it's how much pressure is in a solution. Okay, osmolality. I like to think of it like how thick is it, So when you hear me say something's thick, you think, okay, that's got more particles in it. It's thicker. Like corn syrup is thicker than Diet Pepsi. Okay. So we're reflecting here to think about the total concentration of solutes in a solution. Now, there's the normal range. I'm never going to ask you that, okay? So don't worry about it. Where it becomes important is when you were looking at lab results with one of your patients, you might want to see if this is high or low. So if someone has a high serum osmolality, their blood's going to be thick, or they're going to have less water on board, or they might be dehydrated. But I'm not going to ask you that normal range, so don't worry about that. And that's the end of that. So I think that finishes up everything we wanted to talk about in terms of transport mechanisms. Cam clip number 4.